Chapter 7 is all about continuous probability distributions. Last chapter we were all on discrete, and binomial is a type of discrete, and so we had a nice bar graph or histogram sort of thing to represent those discrete ones. This time, continuous variables deserve a continuous curve, and so we have infinitely many different x values with each y value standing for the probability of those. And normally we're going to talk about like ranges, and so we talk about this entire range. We can't actually add up all the bars, so this is kind of a calculus idea. This area that's under the curve represents the probability of something happening between here and here. We'll talk more about that, but since chapter 7 is mostly about these normal distributions, we should probably get to know the normal curve a little bit. The normal curve, it's nice and symmetric. Maybe we'll write that down first. It's nice and symmetric. And that line of symmetry, can you guess which point, which x value is going to have the highest value, the highest probability? The expected value has the highest probability. And so we're always going to have the sort of the middle of that normal curve on the x-axis is labeled mu. The y-axis, it won't always show up, but the y-axis is always assumed to stand for the probability. So next thing is we can't add up all the bars to equal 100% probability, so we say that the area under this entire curve adds up to 1, which stands for 100% probability. So we just say that that area represents the probability. This is for my pre-calc kids out there. I know it looks like this normal curve is touching this axis, but it actually never touches. That is technically a horizontal asymptote. Horizontal asymptote. Which just means that gets closer and closer and closer to 0, but the probability really never equals 0. But it gets so low that it starts rounding to 0 basically, but technically that's a horizontal asymptote. And the last thing, this is sort of for my calculus students, but all of you will understand this. Do you see this point right there? There's a matching one over here with the symmetry. But do you see what happens at that point, how the curve is sort of shaped up like a cup right here? And I would also consider this part over here to be up like a cup. And then I call this part down like a frown. It's just sort of the curvature of the normal curve. Well, where it changes from up like a cup to down like a frown is right here, and they call that the inflection point. And it turns out that that happens at kind of a significant value. If you go away from your expected value by a certain amount, and guess what the amount is? If you go this way by sigma, by the standard deviation, if you go down by sigma, or if you go up by sigma, oh, that's cool. That's where the inflection point occurs. That's so neat. So it happens 1 standard deviation from the mean. In case you were trying to draw a really pretty curve, you would know where to switch it from up like a cup to down like a frown. I think that's all we want to talk about for the shape of the curve, but now let's talk about just some amazing properties that it has. Remember Chebyshev and how he says that as long as you stay within 2 standard deviations of the mean, at least 75% of the data, or in this case the probability, would be within 2 standard deviations. So that's what these dotted lines are. They're standing for dotted, or for standard deviations. So here's that 1 standard deviation away, that inflection point. Well, there's actually an even stronger rule than Chebyshev. If you know it's a normal distribution, it's called the empirical rule. It says 68% of the data is within 1 standard deviation of the mean. So remember, we're talking about the area, like I said, the area under the curve. So if I go down from the mean or up from the mean by 1 standard deviation, I can expect 68% probability between those two values. So we should label that. So between here and here would be 68%. And that's split evenly if you wanted to put down the 34 for this piece and the 34 for this piece. And then the next one, the 2 standard deviations. If you go within 2 standard deviations of the mean, how much of that probability is taken up? 95%. And here's another one. Within 3. We're getting to practically no chance of being outside this range. It's a 99.7% chance that you're going to fall in that range. It's very unlikely that you would find any probabilities outside of that range. Also, these are rounded, so if you see slightly different answers somewhere, it might be because of the rounding. Let's talk about a good example. The average lifespans of 2 brands of traditional light bulbs are both 1,000 hours. Brand A has a standard deviation of 150 hours and brand B a standard deviation of 110. And the lifespan is normally distributed. So if we made this the brand A graph and this the brand B, it says it's normally distributed, so we're going to use the same curve for both of these. And, you know, depending on the situation, it might look higher or lower, but we're mostly concerned about the x-axis. And do you remember what goes in the middle? The expected value, or the average. We would expect the average light bulb, actually for both brands, to be 1,000 hours, right? Okay, and so then what are these other tick marks? Well, we like to mark these other tick marks at the standard deviations from the mean. And so brand A had the standard deviation of 150, so what's 150 away from 1,000? Another 150 away, another 150, and then going down the same thing. And then on brand B, it's going to look a little different because the standard deviation is 110, right? So each of these little marks is going to be 110 hours from the mean. And in just a minute, we'll see how we can use this to answer these questions. So once again, the spacing of those is just related to the standard deviation. Here's a great question. What is the probability of a brand A light bulb lasting between 850 and 1150 hours? 850 and 1150. Remember that the probability is represented by the area under the curve. The entire curve being a probability of 100%. What percent lies between 850 and 1150? That was the empirical rule on the last page. We know that it's going to be 68% of the light bulbs will last between that many hours. For brand A, lasting between 1150 and 1300. Oh, we're going to have to think a little harder for this. All right, so what do we know? We know that if we go all the way out 2 standard deviations away, that's 95%, right? And we know that this was 68%. So how much is just in this chunk? You think we can figure that out? Alright, well I know that if I split that down the middle, 68 split down the middle is a 34%, right? How much would be in here? So half of 95 minus 34, I'm getting that there should be 13.5% in that little area. In fact, I think it might be worth going back to this diagram and labeling what each little chunk of area stands for. So you had the 34%. And so if you kind of do the math and you split things evenly, this little bar between the first and the second standard deviation is going to be 13.5%. The next little chunk is 2.35%. And then what's left for those dinky little numbers down there? Well, we only had 0.3% other than that 99.7, so you wind up with 0.15% for those little chunks down there. We're going to be using those enough that I think that's worth labeling on your graph here. Oops. So we are going to say 13.5% for this one, for a brand A. Going to brand B, what's the probability that it lasts longer than 1220 hours? So that's 2 standard deviations above the mean or longer. So that was the 2.35% and the 0.15% added together, right? So that should be a 2.5% chance that you'd find a light bulb that lasts super duper long. Those are the types of problems that I want you to try, and I'll answer questions next time. This is just the coolest thing you're going to see all day. If you ever actually wanted to make a graph of that bell-shaped normal curve, this is the equation that you would type into your y equals. It has an e in it, it has a pi in it, it has a square root, it has everything. And on top of that, do you see the mu and the sigma? Because the shape of that curve, they all kind of have the same shape, but the height and everything depends on the mean and the standard deviation. I just think that's the coolest thing.